Hey Physics, Mr. Hausman here. We're going to take a look at what I'm going to refer to as a level 2 compound circuit to analyze, also called a combination circuit, because what you'll immediately recognize is that while it's getting a little more complicated, you recognize parts of this circuit. And we're going to use brackets to show you what I mean. If I say just look at R3 and R4, no one has any hard time figuring out that that's series. And in fact, you know how to add those two together. It's just 48 plus 6, or 54 ohms of resistance. Then if you look out a little farther, we're using the inside to outside method of kind of grouping together resistors. And also notice that we now have gotten to a junction. There's a junction right here, and it recombines here. So if you see a junction, then you know that must be a parallel part. And this was series. So 54... do you guys remember that that was the sum of the series? Plus 27, I know how to add those, and we're going to show that in just a minute. And then if you look at the whole circuit, if you kind of step out, I actually use my hands, kind of like parentheses, and I say, now let me look at the whole thing, and you'll notice that that's now a series circuit, because the parallel portion is now embedded in series with R1. So that's how you kind of frame it. And does that mean you immediately know how to solve it? Well, let's kind of break it down. So do we know the voltage of our battery? And the answer is, yep, we have 120 volts. Without any voltage, we don't have any current to speak of. And so the resistors wouldn't do a thing, but we have a voltage. And we know we're trying to find the equivalent resistor of the whole circuit. And so we can't do that in one step. There is no one formula that allows you to do that. So what we're going to do, this time, we're not going to redraw the circuit, but we are going to say that we have to sequentially add R series, and that's really R3 plus R4, and that's 48 plus 6, or 54 ohms. And then we're going to keep going wider. Remember we said we were going to go to parallel. So R parallel is going to be R2 to the -1 power plus R3, 4 to the -1 power. And so let's put in some numbers. 27 ohms to the -1 plus 54 ohms to the -1 power. Grab your calculator. 27 to the -1 plus 54 to the -1. And you get 18 ohms. Follow along with, right? Now, do you remember that we said it's going to be R series? And see what I'm doing? I'm indenting. And I don't know if you like that. Maybe you want to prefer to line it up on the left-hand margin of a page to just keep it straight. But I find that basically I'm showing my process. I'm showing step 1 was series, step 2 was parallel, and let's finish with R series. So now we're doing R1 plus R2, 3, 4. And notice I didn't use any negative exponents because in series, you just simply do arithmetic. So 12 plus 18 is nothing more than 30. The total resistance of this entire circuit, what's the equivalent of simplifying all of this? The R equivalent for this whole circuit would be 30 ohms. And it's really nice that we've set it up that now we can do Ohm's law and we do V over R to find the I total, 120 volts over 30 ohms. And you get 4 amps. Okay. What do we do with that? Do we immediately go put that into our RVI table at the top? And the answer is we can't. The only time you can give everyone full current, maybe that 4 amps, is if it's a series circuit. The only time you can give everyone the full voltage of the battery is in a perfectly parallel circuit. And this is compound. So what we do, and this will help you, is you simply write in or draw in where is the 4 amps working. Well, the 4 amps is by the battery. Now, I have the luxury of being able to erase some of the things I wrote before. Let's get rid of these parentheses. You could do the same if you're using pencil. Because now we have a nice clean circuit to work with. So where did we say the 4 amps would be? The 4 amps, and let's make it a black puck for, hockey puck. And then let's make that 4 amps. I call it a current puck. It would be also 4 amps when you return after all the junctions, all the splits are done. Where else would it be 4 amps? It would be 4 amps right before the junction splits, right? We have a current split here at that node, at that junction, and it comes back together here. But what we've just done is we've unlocked the next step. And the next step, therefore, is, we now know that R1 gets all 4 amps. And therefore, you don't pause, you don't say, I'm going to go figure out the other currents. You immediately finish that row using Ohm's law. Let's get the voltage drop across R1. And the voltage drop across R1 would be 4 times 12, or 48 volts. Now, every time you say, I don't know where to go next, you know what the answer is? Draw in what you just figured out. Because if you can visualize it, 48 volts right here, and it does make the picture a little busy. Maybe you want to use color. So 48 volts, and you're saying, but Hausman, you taught us to use highlighters, right? We color code our pathways to show voltage. I thought you said it was 120 volts. No, what we're saying is that the voltage drop, right? Our delta V at the first resistor is 48 volts. So we now know that we have to be at a lower voltage when we go to the next resistors. And let's use maybe a yellow for that. Notice the voltage stays the same on both of those pathways. Remember, let's do blue while we're doing it. We're kind of doing some work to stay organized, right? And by stopping, writing in the 48 volts, color coding, do you notice what you just discovered? You just discovered right here at R2, you have a really easy segment here. You realize now that 120 volts minus 48, and then you know it's 0 volts on the other side, because blue represents low voltage, low potential. Now what you realized is that the voltage drop here across R2 has to be 120 volts minus 48 volts, or how much? 72 volts. So the yellow line must represent 72 volts, then to 0. So the delta voltage across the 27 ohm resistor is 72 volts. Finish a row, right? There's no stopping. I equals V over R. You won't be able to read that, V over R. And therefore, we're going to get a current equal to 72 volts over 27 ohms, 72 over 27, 2.66 amps. 67 amps. Okay, great. So maybe you're still going, what's next? And so when you don't know what to do, you go and draw in, where is that 2.67 amps? The 2.67 amps is anywhere in the pathway with R2. Now you're starting to get it, that now you can see that if 2.67 amps go straight after that node, then how much current has to be going down through the lower pathway? We have 4 minus 2 1/3, and we get 1 1/3. I like to double check. Because the total current at a junction before and after, according to Kirchhoff's junction law, is that you have to have your current add up. So 4 minus 2.67 is 1.33. And then we finish V equals IR, 1 1/3 times 48, 64. 1 1/3, we're going to do it for both resistors, 1 1/3 times 6 is 8. It rounds off to 8. It's 7.99, depending on how many digits you carry. And now we can kind of see if 64 plus 8 equals 72? Does 64 plus 8 equals 72? And the answer is yeah. So the voltage drop across R2, or R3, excuse me, was 64 volts. The voltage drop across here was 8 volts, and they added up to the voltage drop of the 72 volts, which is exactly what we'd get for R2. And look at the color coding. Now, if you want to be particular, you may have noticed that I never gave an intermediate color for here, and so if that compels you, make it green. So you've now figured out how to analyze a level 2 circuit.